You know, when you see a system of linear equations, your first thought is probably, okay, solve for x and y. But what if I told you it's actually a visual story? It's a story about how two simple straight lines can interact on a plane, how they can meet, how they can avoid each other, or how they can actually be the same line in disguise. Let's dive into that story.
So let's start with a really simple question. Forget all the algebra for just a second. Imagine you have a blank canvas, a flat plane, and you draw two perfectly straight lines that just go on and on forever. How many ways can those two lines actually interact with each other? It sounds complicated, but it turns out there are really only three possibilities.
Okay, so the first and honestly the most common thing that can happen is this. They just cross. They intersect at one and only one specific point in space. This single point where they meet, that's what we usually think of as the solution to a system of equations. Now, what if the lines have the exact same steepness, the same slope, but they're just shifted apart? Well, in that case, they're parallel. It's kind of like two lanes on a perfectly straight highway. They run alongside each other forever, but they will never, ever touch. And if they never touch, that means there's no point they share in common.
And the last possibility is a little bit of a trick. What if you have two equations that look totally different on paper, but when you graph them, they actually describe the exact same line? Well, then the lines are just lying right on top of each other. They don't just share one point, they share every single point along their entire length, an infinite number of them.
All right, so we have these three simple pictures in our heads now: intersecting lines, parallel lines, and identical lines. Now let's give them their proper mathematical names. We have some specific vocabulary to describe these situations, which helps us talk about them without needing to draw a picture every single time.
The first big term is consistent. A system is called consistent if it has at least one solution. So think about our pictures. This word covers two of them, right? It covers the single intersection point because that's one solution, and it also covers the identical lines because they have infinite solutions. As long as there's a solution, any solution, it's consistent. So the opposite of consistent is, you probably guessed it, inconsistent. This one's pretty easy to remember. It means the system has absolutely no solution. Zero. Zilch. This term perfectly describes our picture of parallel lines. They never meet, so there's no point of intersection, which means no solution. All right, now for our second pair of terms. Equations are independent if they each represent their own distinct line. They're basically two separate entities. This is true for our intersecting lines. They are clearly two different lines. And, maybe surprisingly, it's also true for our parallel lines. Even though they have the same slope, they are still two distinct separate lines. And finally, we get to dependent. This is our special case. This is what happens when two equations are really just the same equation wearing a clever disguise. Every single solution for one equation is also a solution for the other, precisely because they represent the exact same line. Okay, this slide right here, this pulls it all together. Let's just walk through it. Look at that first row. If you find exactly one solution, you're looking at intersecting lines. And what do we call that? Well, since there's a solution, it's consistent, and since they're two different lines, they are independent. Now, row 2. If you find no solution at all, you've got parallel lines. No solution means it's inconsistent, but they're still two separate lines, so they're independent. And that last row, if you find infinitely many solutions, it's because it's the same line. It's consistent because there are solutions, but because it's really just one line in two forms, the equations are dependent. All right, so the pictures and the vocabulary are super helpful. But let's be honest, drawing a graph every single time isn't very practical. So how can we figure all this out just by looking at the algebra? Well, it turns out the equations themselves leave behind some massive clues. Let's watch this play out with an example. We'll use substitution here. We're going to take that value of y from the first equation and just plug it right into the second one. Okay, so we substitute, and then we distribute the 4 across the parentheses, and wait a minute. Look what happens. The 5x and the negative 5x, they just cancel each other out completely. They're gone. So after all that work, our variables have completely vanished. We're just left with this statement. Negative 20 equals negative 20. I mean, it kind of feels like we went nowhere, but this right here, this is actually our first major clue. So what does that mean? When you do all the math correctly and the algebra boils down to a statement that is just fundamentally always true,
What is the system trying to tell us about those two lines we started with? And here's the big reveal. Getting a statement that's always true, like -20 equals -20, is the algebraic signal for dependent equations. It means our two equations were secretly describing the very same line all along. And that tells you the system is consistent and has an infinite number of solutions. Okay, round 2. Let's try another system. We'll do the same thing. We'll take 2x minus 2 and plug it in for y in that first equation. That gives us -2x plus 2x minus 2 equals 6. And look, it happened again. The -2x and the plus 2x cancel each other out. But check out what we're left with this time.
This time, our final statement is -2 equals 6. Yeah, I'm pretty sure that is just not true. It's never true. It's a mathematical contradiction. It's just false.
So, what's this clue telling us? If the algebra leads you down a path to a statement that is fundamentally impossible, what does that say about the relationship between the two original lines? And that's our second big clue. Getting a false statement, a contradiction, is the algebra basically screaming at you that this system is inconsistent. There is no possible value for x or y that could ever make -2 equal 6. And what does that mean for our picture? It means our lines are parallel. They never meet, so there is no solution. This slide is the master key, the ultimate cheat sheet. It connects everything we've talked about. Let's look. Top row, you solve the system and you get a normal answer, like x equals some number, y equals some number. That's your one solution, your intersecting lines. We call it consistent and independent. Middle row, the variables disappear and you're left with a true statement, like 5 equals 5. That's your infinite solutions, the same line, consistent and dependent. And the bottom row, the variables disappear, but you're left with a false statement, like 5 equals 2. That's your no solution case, your parallel lines, inconsistent and independent. Okay, to wrap this all up, let's take a step back and look at this whole topic from a completely different and frankly really cool perspective. We've been thinking about equations as lines on a graph, but what if there's something else entirely? On the left, you see what we've been doing this whole time. It's called the row picture. Each row is an equation for a line, and we're looking for where those lines intersect. Simple enough. But now, look over to the right. This is the column picture. Instead of reading across, we're grouping the numbers vertically, into columns, into vectors, and we're asking a totally different question. What combination of the x factor 2, 1 and the y factor -1, 1 can we use to build the answer vector 1, 5? The goal isn't to find a point. It's to find the right recipe. And this is the absolutely incredible part. The solution is the same, x equals 2 and y equals 3. But what that answer means is completely different depending on which picture you're looking at. In the row picture, 2, 3 is a place. It's the single point where two lines cross. But in the column picture, 2 and 3 are like ingredients. They're the recipe. It tells us we need to take 2 of our first vector and add it to 3 of our second vector to perfectly build our target. It's the same numbers, telling two completely different geometric stories. So which is it? Is the solution a point where two lines cross, or is it a recipe for combining building blocks? The beautiful answer is, it's both. And this just shows you something amazing about math. Sometimes the deepest understanding doesn't come from finding a new answer, but from finding a brand new way to see the answer you already had. Pretty cool stuff to think about.